也是必须开实体课。行，你们忙，还差一个。
还差一个。All right, yeah, I guess I'll wait for a while before I actually start it. Yeah, but brief overview about today. Yesterday we finished this classes and object chapter. There will be a assignment releasing, I think pretty much today, maybe later. And yeah, so it will be about classes and object for sure. Yeah, applying the knowledge of what you learn in terms of class and objects. Maybe inheritance or encapsulation or those kind of idea. And in terms of plans for today, we are going to talk about algorithms. Algorithms. There are lots of algorithms to talk about. Mostly sorting, because it could be one of the fairly simple or like easy to get introduced algorithms. And yeah, so that is the plan for today. Okay. Okay. Let me actually get started. All right. So a brief review about yesterday. We talked about inheritance and we talked about polymorphism. So inheritance means that it can extend a superclass, and then you will just have all the properties, all the fields that and all the methods that a superclass have, and then you can define something else yourself. Okay, so yeah, when defining a Python class, don't specify. Yeah, if you don't specify what the superclass is, it will be object class. Okay, so that is done automatically. All right, and the subclass or child class is a special case for superclass. For example, if the superclass is fruit, then the apple can be its subclass, right? So it is a special case of fruit. So it is apple. Okay, for child class perspective, it is extending the superclass. From superclass perspective, it is deriving the subclass. So yeah, and then you can have different perspectives, but it is eventually describing the same thing, right? And yeah, here is an example. You can have a class fruit, and then you can have an intro function, and then you can have a class food, you can have a taste function. Then you have a apple class, which extends both of those two classes, and you can try to set this field weight, and then you can call both functions, info and taste. Okay, and yeah. But once you construct it, then the Apple object has the method info and taste. And to keep in mind, most of the language only support single inheritance, even though Python supports multi-inheritance, but it is not recommended to use unless it is necessary. Okay, unless it is necessary. Okay, this is because different classes have sometimes have the same method, and it will overwrite the repeated method. Yeah, and then here is the code which illustrate the problem. you can have this class called item, and then you can have an info, and you can have class product, and it also has the method info. And then you can when a class mouse extends both of those two classes, and if you call this function m.info, then it will only call whatever is first in the list, in the extended list. So in this case, product is in front of item. So the m.info will just call the info method in the product class. Okay. And then, the item class, the info method in item class is not being called. Okay. And you can have overriding methods from superclass. So, sometimes superclass does not provide what you want exactly, right? Because we are creating a subclass, so subclass has to be somehow different than the superclass, right? Sometimes there is a given some method that the superclass has already defined, but for a subclass it is not the case. You have to rewrite it or like override it. Okay. So yeah, most of the time subclass needs to add more methods than the superclass. Sometimes we also need to overwrite some of the methods from superclass. Okay, so this class called bird, it has a function called fly, and then print out can fly. And you can have a class ostrich which extends birds. Ostrich is a kind of bird as well, but you can change the fly function because it cannot fly, it can only run. Okay, and if you have a ostrich object and then you call fly, then it will print out this new function that is defined in the ostrich instead of this function bird, this class bird. Okay. And then after the override, what if you want to access whatever it is originally in the superclass, right? Um, what if you actually want to call a superclass method? So what you can do is here you have a base class full self, and then print full in superclass. And then you have a subclass which extends the basic class. And then you have a full, you rewrite the full method. Okay, that's good. And then you have a function called bar, right? And then you just print executing bar. And then you call this method that you overwrite yourself. And then you call this full function in base class. And then what will happen is, both of those, the function after overwrite or the function, um, the function that is is in the base class will both print. Okay, so that is that. Use super function to call constructor of the superclass. So you have a class called employee, and then you can have it init. And then super is used for I mean, it can be used for anything, but in this case we are using it for constructor initialization. Okay, so to illustrate what the problem is that you have a employee, and then you have a init function with only salary is required, and then work is only printing out the self.salary, and it says it is working. But a customer also needs a favorite favorite product, and an address probably, right? And then this info function just use both of those two methods, most of the two fields to print or to function. And in this case, if you do m equals manager blah 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 blah, which gives the salary, and then if you call work function, it works perfectly because you have this field of salary. But if you call this method info, then it will not function properly because it will require argument for favorite and address. Okay. And if you try to switch sides, switch the order of the superclass, then initialize it with salary will not work anymore. You can only initialize with product and address, but also you cannot call this work function here because there's no salary provided, so the work function cannot function. Okay. And in Python, the rule is if subclass rewrites the constructor of a superclass, it has to call the constructor of the superclass. Okay, so you cannot do like something like self.salary is equal to salary, self.favorite is equal to favorite. What you have to do is you will use this super, which directly bounded to the first superclass that is in your bracket, and then you provide those parameters, right? You have also taken salary, favorite, address, and maybe a name, right? And then you just call super in it, and then with salary in it, and then you can call customer.init, and when it is customer, then you need to be careful of if you need to pass in a self, right? Because in terms of because this is not automatically bounded by the compiler itself, so you will have to pass in this self object yourself. Okay, so that is something that you can easily find out when your code does not compile. And then you can also have an extra field, right? And you can do a self.name is equal to name, right? And then after that, you can pass in, right? You can pass in manager with salary, favorite, address, and name. Okay, and then you can call work function, it works perfectly. Call info function, it works perfectly. You can also access this name property. Okay, so in terms of, yeah, when you want to add a method to an object, what we mentioned in previous lecture is using the method type function. But what if you want to add a method to all instances, and then you want to do something like this? So this is the following. You use class cat, and then you have an init, and then you have a walk function, which is outside of the class, and then you want to add into it. Okay, so you will have both of those two objects, and then you can define it like this. So it is sort of like a class variable / class method, and then cat.walk is equal to walk function, right? And then as I said, it has this parameter, so it is automatically bounded to any object. And then yeah, you can directly call d1.walk and then d2.walk. So both of those two can be function, right? So that is when you have instances from different instances from the same class, but you have a lot of them, And then if you want to add a function or add a method, then you do it on the class instead of going through each of the object and try to add a function. Okay, so that is that. And as you can see here, this is slots. Okay, this is a slots. Slots means that you can sort of also define those variables in a fashion of like object or instance, right? You can use instance dot something equal to blah 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 to sort of define what that value or method is, right? And then the slots is just for defining empty slots, or place a bunch of pigeonholes, right? And then what happened is you can actually fill in as you go on in the program, right? You can fill in those slots. You can say from types import method type, and then you do d dot walk is equal to method type blah blah blah. This is just a method, and the last parameter is the object, the instance, right? And then after that, it compiles fine. And then if you can do ages as well, and then you can actually call this function, and you can see that's printing out. Snoopy is walking slowly. But if you have this slots and you want to define some new variable, this is not allowed. Okay, so if I turn off this quotation line here, then it will give me a error if I run it, but I'm not gonna run it because yeah. Okay. Yeah, so but this will not affect anything in terms of defining a function or a variable using class, right? You can still call class, so which is dog, right? And then dog.bar is a function, and then you just call that function directly. Okay, so that part works good. Yeah. And just to keep in mind, the slots only affects the current class. If there is a subclass from that class, then there's no way that the slots can still affect on those ones. Okay, so you can define a class using type. Right. So usually type is used for getting a type of a specific object, right? And if you get type of a class, then you will receive the type, right? This is weird, but what happened is when the program is defining row, which is the class name, using class keyword, we can treat it as defining an object and with type, and assign that to a row variable. Okay, and then in reality, Python allow user to define a define a not a row, but define a class using type. Okay, so it can actually define a class using type. It can have this, function. You can call it whatever you want, and then it doesn't actually do anything other than print. But yeah, dog is equal to type. Then you're providing the class name, so the class name will be dog, and then you can have what is it inheriting, right? And then because it is a just a normal class, not inheriting from anyone, but object, because object is just a superclass of every single thing. So yeah, it is just object, right? But for a tuple, if there is one element to it, then add a comma so that it is actually treated as a tuple. Okay, then you will have a dictionary for you. You can just create it right away. But if you want to have a dictionary that is created in advance and then pass in at this time, it is fine as well. Okay, so yeah. So in this case, walk is equal to function, and then age is equal to 6. So if you have an instance called D, and then you just type D and type dog, then it will give you the same thing. But if you call D.walk, then it is calling this function above. Okay, and then you can print dog.age, then it will just give you this age 6. Okay, so polymorphism. Um, so polymorphism is the idea of when the object changes and then you call the same method, and then you will have a different outcome. Okay. So as you can see here, you have bird move, right? And then you can have bird is flying freely upon blah, blah, blah. And then you can have the class dog, and then you can also have this function move. What dog is saying is that, dog is running freely upon a field that is provided. Okay. So that is actually provide that. So x is equal to bird, and then if you call x.move bird, x.move sky, then you can see a bird is flying freely upon a sky. But if you call x equal to dog object, and then you try to move on the grass, then you can see dog is running freely upon the grass. But you might think that it is a little bit boring. It is a little bit easy. It is just two different classes have the same methods, and then you're calling it one by one, right? But if you have something like this, so class canvas, then you're having a draw picture function, which in here the shape is will be an object with a draw method, right? And then after doing this, then if you can call draw picture, and then you can initialize the following classes. So rectangle, triangle, and circle, and blah blah blah. And then each of them have a draw function, and then when you call draw picture with a rectangle or a triangle or a circle object passed in, then it will come here into shape, and then shape will call draw, and then draw. This self means canvas, because you have to pass in canvas for it to draw. Okay, so that is like how polymorphism is used. And then as you can see here, like this code is short, right? And then you can do impressive stuff with with this short code. Okay, and then you can have for type, you can have another another use case. This is just checking the type, right? And then you can have this is subclass or is instance, right? And then you can call is instance. It just gives you a object and then a type, right? So that you can call this and see if it is a subclass or in instance of the thing you want to know, right? And then hello can be a string, Hello is also an object because object is anything superclass. And then you can do a subclass string object. So for sure, because again, object is the superclass of everything. But if you have if it is instance hello tuple, then it is not. If you have instance is subclass string or tuple, then it is not. And it basically works the same for the list. Okay, so if you have some time, you can catch it up later. But yeah, bases and subclasses. So this idea of basis is just means that you can call your superclass, right? And it seems like it is a direct superclass, not delete, direct superclass, because class A have object is superclass. Class B also does that, but class C it only has class A and class B. It does not actually give you class. It does not actually give you a the class object. Right. So yeah. So you can also have this called subclasses, and then it just gives you the direct subclass. Okay, and then be careful. Here we do need a bracket, but before we does not. Okay, so that is that. All right, so we are going to exercises. Okay, so those exercises, I don't think it is too hard to finish, but it might still take some time. So yeah, any kind of question in terms of review, or I should directly start um, the um, the exercises. Okay. So it seems like no one have any questions. Then I will get into the exercises. The first one, oh, it is simple. It is just to construct a student class with name, age, gender, phone, address, email, right? And then you just pass in everything in there. When when calling the initialization function, which is the constructor, and then you just provide four methods. One is eat, one is drink, and then one is play, and one is sleep. Right. So this purpose is just to get yourself familiar again, get yourself familiar with class. Class initialization and constructing the class. Like you might think this is easy, but once you code it, then you will find out there are some details that you will usually miss, right? So you have to pay attention to those. Okay, so that was a easy exercise. Let us move on to the second one. Okay, so the second one is create a vehicle class with max speed and max mileage instance attributes. So like two attributes for a vehicle, and then create a bus child class that inherits from the vehicle class. The default fare charge of any vehicle is seating capacity times 100, right? And then that is the time when you actually you can actually write this line of code, right? In the superclass called vehicle, and then you can define a fare function, and then this function just returns what is the fare of that vehicle, right? And then this is sort of like seating capacity times 100. And it says if vehicle is a bus, that is inheritance, we need to add a extra 10% on fulfill because as a maintenance charge. So yeah, the total fee for the bus instance will become final amount equals to total fare plus 10% of total fare. Okay, so like if you want to think about it, then it is 110% of the total fare. Okay, so we can have this fare. This looks simple. It just returns self.capacity times 100. Okay, and then we have a fare function in the bus as well, and then it just calls super.fare, which means calls this fare function in the vehicle, and then you can have amount plus equals to amount times 10 divided by 100. So that means just the total fare, the 10% of total fare, right? Yeah. And then you just sort of print it out. School bus is equal to name, mileage, and capacity, right? And then you can print it out. The total bus fare is 5,500 because 5,000 is capacity, and 5,000 is the fare for any vehicle, and the extra 500 for bus to actually be a special case. Okay, so that is that exercise. And then another exercise is create a time class and initialize it with hours and minutes. And then make a method add time, which should take two objects and add them. So you'll take two objects, which is T1 and T2 in this case. And then you'll make a method called display time, which should print the time. And then you can have a method called display minute, which it should convert hours into minutes, and then actually try to print it out. So we need two initialization parameters. One is hour, one is minutes for sure. Then can have this instance A and B, which is initialized as 250 and then 120, right? So it is the second time is 250 o'clock, and then the first time is the time B is 120 o'clock. And then you can have C equals to at time A and B, right? And then if you try to run this, okay, so yeah, if you try to run this, then the time, if you call add time, so what happened to the add time? The add time, what happened is that you have a T3, right? And then you just sort of start a object, and then if T1 plus T1.minutes plus T2.minutes is larger than 60, which is when you try to add the time, then if it's larger than 60, then you will need to increment 1 in hours, right? So yeah, and what you have to do is here you're doing integer division instead of instead of normal division, right? So what happened is what I did was in a normal division instead of integer division, right? And yeah, so T3 dot hours just gets this value. It can be either 1 or 0, right? Because there is no 60 minutes in minutes, right? There's only 59 minutes in minutes. So it will be either 1 or 0, 1 just for, when it's larger than 60, 0 is just for when it's less than 60. Okay, and then you can do T3 dot hours and then equals to T3 hours and then plus T1 hours plus T2 hours, right? So you just basically add those 3 hours up. And then minutes, you just add both of the 2 minutes, and then you just sort of integer division by 60, and then times 60. So it actually gets you the whole number part, which is in this case is 10. Okay, and then return T3, right? So that is the most difficult method at time. And then you can have this display time, right? This display time just prints out the time in display minutes. Just change it to minutes, and then add a minute. Change hours to minutes and add minutes. Okay, so yeah, that is the output. 250, 120. 120 then gives you 4 hours and 10 minutes. In terms of minutes, it's 250 minutes. Okay, is there any sort of questions or concerns in terms of this exercise? I will probably wait until 10:45 and then begin today's lecture. All right. Oh, okay. Okay, so we are going to start today's lecture. Today's lecture is about algorithms, and the first that is just a little bit of stuff that is left over. I have mentioned it, but since the original class have this as a topic, then I will just briefly mention it. This is not too difficult. So suppose you have a task that is writing a program to help maintaining the seating records for a theater company. Then the auditorium have 25 rows, and each of which have contains 30 seats. So one utility that you will need to provide is tracking which seats are sold, and which can be accomplished by Boolean values. And we could use a single list for each row, which would require a following declaration, right? So you will have, for example, you will have row 1 is equal to false times 30, right? And if you have something multiplied by 30, then it will just multiply the elements in the list and then make the list length 30. Okay, so what is saying here is row 1 is equal to like 30 not false value with like 30 30 in length, so it's a list. Okay, and then row 2 is equal to row 2 is equal to the same thing, and then blah 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 all the way until 25, right? Then you will get sort of like 25 variables, which is if you have so much variables that is doing the same thing, then try to avoid it and try to think of something more clever than this. Okay, so you can visualize it as this. So sold is none times rows, right? So you can have another list to hold, right? And then for each row in range rows, right? So this is sort of like a iterator, and then sold, this number here, and then it is from 0 to 24, right? And then so it is from like, so 0 is 30 a I would say a 30 digit, not 30 digit, but like a list in which length is 30, and then for each row it has the same thing, right? The digit length is 30, right? So this is like so if you have a simple reference, then you can try to print it out, right? So 24 and then 29, that is the last seat that you have. So and then the idea is something like this. So the results of declaration are shown in the following program, which is like sold is a list. It is a 2D list. So in terms of 2D, it means that there is 2 dimensions, right? In for the list. So it is also the idea of list in a list, right? So you can have this sold with element 0, and then you don't know what the element is. You can treat that element as a whole, right? As a black box, and you can later walk into that black box, and what is in there? It has a false list with like 30 in length. Okay, so that is that, and then that is for each row it has the same thing. Okay, so in this case, then this will be a 2D list. Okay, and then to traverse through a 2D list, two-dimensional list, just as for the statement is useful for traversing a one-dimensional list. We can use nested for loops to traverse a 2D list. Remember, our current sold list contains 25 lists representing each row, and then 30 elements representing each column. right? Or i.e. seeds, right? And then the output, you can do something like this for row in sowed, right? For each row in sowed, which will give you like looping through the elements in sowed, right? And then after you get one element from sowed, then you get into the second for loop, right? And the second for loop, because uh, the element of sowed is also an array, so you can not array, a list, so you can also iterate through it, right? For seed in row, then you should sort of print seed, right? And then you can print like true or false values to indicate if the seed has been sold or not, right? And then there's also a index way, right? So you can do for row in range length of sowed, and then the length of sowed is just how many rows there are, right? So it is 25. All right, so the length of sowed row is 25, right? And then for seed in range blah, right? For seed in range length sowed row, right? And then you can have sowed row is just this current row that you're looking at, and you just get the length of that, and then the length will just give you how many columns are there, and then you just iterate through each seed, right? And then you can just do, if you want to set it equals to true for each one of them, then you just do sowed and then bracket row and then bracket seeds as equal to true, right? And then because rows and seed are changing every single time, so um, it will not only um, change a fixed seed. Okay, so that was 2D list. That was not very difficult to actually look at and then to actually deal with. Okay, so what we'll do is I'm sort of officially starting to introduce this idea of data structures and algorithms. Okay, and the first things first, in terms of data structures and algorithms, the first thing we will look at is this topic called asymptotic notations or asymptotic analysis. Okay, and what is asymptotic analysis? It is sort of a algebra way to tell how fast it is, how fast your algorithm is, right? So, for example, you're sort of defining an algorithm for a specific task that you want to solve, right? And then you can use asymptotic notation to express how fast your algorithm is. It can be like O1, ON, or whatever. That one I will introduce later what that is. Right. So yeah, asymptotic analysis is an algorithm referring to defining the mathematical foundation or framing of its running time performance. Okay, so that means because it is a mathematical foundation and framing of the runtime performance, then we will sort of have three main metrics of a like three main metric for asymptotic notation to analyze an algorithm. Okay, so it has most of those three stuff. So which first one is called the best case, right? So when the input is, very nice or very ideal, or for example, if you are dealing with a sorting program, dealing with a problem, and then the original list that it's giving you is sorted, so you don't have to do any work, right? So that is some stuff that we need to consider about like the best case, right? The best case is just when everything is the best scenario, then how complicated your algorithm is. And average case is more general, and if you have heard the idea, it's called not overfit. And overfit is just means that is specifically to a given set of input, right? So if you have your average case, that means that, for example, you're given a random list, right? You're giving a random number list, and then you don't know whether it is sorted or not. You don't know what is the order. You just know it is a list needs to be sorted, right? And then you just perform your algorithm and do whatever from there. Okay. And then the last one is called the worst case scenario. And then sort of, for example, if the list is totally reversed, right? And then you are sort of having to, flip each of the number, and see, how that performance is, and that is called the worst case scenario. Okay, so this is like the max time required for program execution. Okay, so after introducing those ideas, you can see this. You can see there is like three kind of notations that we are going to use, or for you guys to know. The first notation is called big O notation. You just read out loud the letter O, right? Okay, so it is called the big O notation, right? And then the second one is called big omega notation. The third one is called a big zeta notation, right? And then big O notation just means it is a formal way to express the upper bound of an algorithm running time. Okay, so that is like limited to whatever is the upper bound, or the upper limit, like how fast it's gonna go and how far it's gonna go. Sometimes it goes on forever and forever, then this on will be really large. Sometimes you just flat out, this function just flat out, or this method only takes like constant time, right? Then that big O notation will be pretty small. Okay, so as you can see the graph here, for the function f of n, big O of f of n is just g of n, right? And then the definition is that there exists c is larger than 0, such that n0 such that fn is less than c times g times c times g of n for all n is larger than n0. What does that mean? Like, I don't always like the mathematical notations. They are hard to understand, but think about this. So after a certain, so this is x and this is time, right? After a certain x on the horizontal axis, you can find a point here where g of n is always larger than f of n, right? And it is this point k here, is in this case c, right? So there exists k, so it is k, but like after k, g of n is always larger than f of n, right? And this is just a little curve to analyze. And then big omega notation is this sort of corresponding idea. You have big O and then you have omega. So omega just means it is the lower bound of the algorithm running time. So I am just gonna not repeat myself there. And then omega notation is not usually used because sometimes as engineers or software engineers, or like programmers, you always have to be careful of the worst case, right? And then like your customer will need something that will always work, right? Something that does not go on forever, right? So that is something to get concerned about. Okay, and then this definition is pretty similar. The only difference is g of n is less or equal than c time c dot f of n. Yeah, I think c dot f of n is just this f of n after c. Okay, so that was a mistake of me saying it is multiply. So it is sort of after c. Okay, so the Seda notation, just is a formal way to express both lower bound and the upper bound of an algorithm's running time. So you can say that for Seda notation, it means that your function f of n is actually bounded within range, right? So it has lowercase, or lower bound of something, blah blah blah, and then you also have a upper bound, right? And the Seda notation is just that it can bound this function very tightly. Okay, and then yeah, sometimes Seda notation and O notation has the same value, right? Because upper bound could be like lower bound as well, right? It is just that your algorithm might perform very constantly, and then it is just a Seda notation is the same as this big O notation. Okay, and then here is a table. What we usually use is big O notation because we always need to consider the worst case scenario. So those are all in worst case. Okay, so what is the easiest, or what is the most the best performance of O? Because O is the upper bound. It means that your algorithm cannot be more complicated than the upper bound, unless you did the upper bound part wrong, right? But yeah, that means that algorithm is at most maybe in this constant time. So constant time is the smallest. It means that it is the algorithm is a number, right? And it can be let me give you an example here. So constant time. What is a constant time? Constant time means, for example, if you have a line of code, let's say some variable is equal to x plus y, right? That is considered as constant time because you don't really know how long time it takes, but it will finish and it will definitely does not take long. It is just very very fast. So that is constant time. And then even though it is called constant time, you don't have to be exactly the same in terms of time, right? Because you can have multiple operations, and you have multiple you're probably doing it on a different machine or whatever, but it can be still a constant time. That just means that the time complexity is constant, not the actual time is constant. Okay, so that is that. Log. Log just means it is 2 to the power of something. Okay, in computer science world, if you don't write any kind of subscript to this symbol log, then it is automatically means it is base 2. Okay, because binary, right? Computer does not do well in terms of decimals compared to binary. Okay, so log. Let me give you an example. If you I don't know if you have heard of binary search, okay? But it is basically saying that you have a number in a sorted list, and then you will have to find where that is, or you will have to guess a number, right? If you want to implement a number guesser. And then what is the fastest way that you want to get, right? So you'll probably ask, so here's a game, right? I have a number in mind that is from 1 to 100, and then you sort of I sort of want you to guess what number it is. Okay, so you just sort of have a number in mind, and then you probably start to do things. Let me illustrate you with like drawings. Let's say this is 1 to 100, right? And then I might have a number somewhere here, right? I don't know what the number is. I have to guess the number. Okay, then what we will do? What we will do is oops. You do something like this. So you have 1 here is 1 to 50, and then you do 51 to 100, right? And then if you can ask, does this have the number that you want, right? Or does this have the number that you want, right? Then the gamer will just tell me yes or no, or blah blah blah. And then if I for the first half, if he said yes, then I will further break down into 1 to 25, and then 25. I checked 25, so 26 to 30. right? So this is actually called log n time. What happened is that you have a 100, right? And then you will just need to at most do 6 or 7 this kind of cuts, and then you can just get the number that someone else is guessing. Okay, so that is pretty cool. And then if you have like non-programming friends, or like you can sort of demonstrate this to them, and then make some friends and stuff. Okay, so you can you can the next is linear time. What does linear time means? The easiest one is a for loop, right? So if you have a length n, right? So it could be 100, it can be 300, it can be lots and lots, right? And then you just keep counting, right? You just keep counting the ends, right? For n is equal to 1, blah blah blah, n is equal to 2, blah blah blah, and then all the way until the end. Okay, so that is linear. N log n, I'm not going to talk too much about it, but n log n is just a big improvement from n squared, right? So quadratic, cubic, polynomial, exponential, right? So quadratic just means that if you have ever seen the quadratic function, you just take the left side, the right side, the positive side, and then draw that. You can see it is a parabola that goes on forever and forever, right? And then there is no such a place exists on yours for this. So yeah, and square. So you can also do an n cube, right? And this is the same. And the polynomial, exponential, those are just growing faster and faster and faster. And then just go up high in the sky. Okay, so yeah, that is that. And then those asymptotic notations are ordered by they're ordered by complexity. So this is less than this. It's less than this, less than this, less than this, less than this, blah blah blah, all the way down there. So exponential is the largest. The polynomial is the second largest, and then cubic, quadratic, right? And then those the previous ones are constant, log, linear, and log n, right? Those ones are as you walk up the table, then you will see those performances are actually getting better and better. Okay, so yeah, that is a short introduction to asymptotic notation. I could go into some details, or not details. I could go into. Oops, sorry, I just click pause sharing. So I'm just gonna assume that if anyone cannot see my screen, just let me know. Okay. So yeah, and that goes up and goes up, goes up. So it is becoming better and better. Okay. So in terms of big O notation, yeah, I think I have pretty much explained this, but I guess I will show you guys a video anyway. Oh, here's the article, not a video. There is a video. But yeah. So if you can see this, I posted a Wikipedia page for big O notation, If you're interested, you can go ahead and read that post, and then try to figure out examples. And actually, have some real examples here. So if you have fx is equal to 4, 6 times 4 x to 4, 3 times x to 3, blah blah blah, and then you can just break you sort of break up in terms of terms, right? And then you just pick the highest term for big O. Okay, so yeah, that is the big O notation. Yeah, I mean, anyways, if you're interested, read it out loud, or read it on your read it on yourself. Right. So the most frequent ones that I have talked about, constant time. This means it costs 0 time. Then and then you have log n time, which is base 2. It is very fast compared to n itself. Okay, and then you have on, and then you have on log n. So that is n times log time. It is so much better than n squared. Okay, then you can also have exponentials. But yeah, I'm gonna show you a video about
I didn't realize how many mistakes I was making in English until I started to use Grammarly. It's like having a proofreader and an English teacher.
Today we're going to learn about Big O notation. So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine. Rather, we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n. This is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page. We ignore or drop low-order terms when they're dominated by high-order ones. Take a minute and study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the Big O of various important algorithms. Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we have the following line of code. This basic computer statement computes x, and notice, it does not depend on the input size in any way. We say this is Big O of 1, or constant time. What happens when we have a sequence of statements? Notice that all these are constant time. How do we compute Big O for this block of code? We simply add each of their times, and we get 3 multiplied by Big O of 1. But remember, we drop constants, so it's still Big O of 1. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. We know the print statement is Big O of 1. This means the block of code is n times Big O of 1. In other words, Big O of n. Here's another sequence. The first line we know, again, is Big O of 1, and the for loop is Big O of n. The total time is the summation of these two, but remember we drop low-order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop dominates the runtime. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n, which gives us big O of n squared. Let's do two more examples covering everything we've talked about. Say we have the following block of code. What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the three. The nested for loop dominates here, so we get big O of n squared. How about this if-else statement? Pretend the sequence of statements in each clause have already been deduced to the big O's shown. We talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime, which happens to be big O of n squared. I hope this gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a large impact. Lastly, for the same reason, be cognizant of best and average case. Depending on your application, this may be more applicable for your algorithm. As always, thank you for watching. Please subscribe if this helped.
Yeah, so this video explains more. I think it definitely explains better than me in terms of big O notation, right? And you know, a rule of thumb is if you add a bunch of big O's, you just pick out the largest. If you multiply a bunch of big O's, then you know, make sure that you know, it is becoming like n square or n cube or something like that. But anything that's larger than n square is considered as pretty bad. Okay. And then what else? Yeah, and then, yeah, that is pretty much it. So after those two, we are going to talk about this first sorting algorithm, or we're just gonna talk about sorting algorithms. So I have a Wikipedia page for you. Okay, so if you scroll down to comparison sorts, you can see a table here. You can see a table right here, which gives you you know, a whole bunch of sort. Yeah, there's a whole bunch of sort out there, but we are just gonna specifically look into a bunch of them, not all definitely, and yeah. So you can see here, you know, this bubble sort we talked about yesterday. And then what I prepared for today is bubble sort, selection sort, and insertion sort. Maybe we don't get the chance to finish all of them, but we will see how it goes. Okay, so but yeah, here, those ones are asymptotic notation for the algorithm's case, right? And then you know, you can have this best case, or you can have this worst case, and you can have this average case. And then you know, in terms of software dev students, then those ones will, I would say, probably pop up in your interview. So just be careful with that. And then, yeah, as you can see, most of the algorithm, on average case, will be n log n. So you know, n log n is also considered as a good case for any kind of algorithm, or this is that is good enough n log n. Okay. All right, so we are going to talk about bubble sort. Okay, so I have showed you guys a hungry dance video yesterday. I don't know if you guys enjoyed it or not, but you know, the idea is when it comes to algorithms, the most important thing is sorting. No, not sorting, but the most important thing is visualization. So, as long as you know how it works and you know what to do, then the coding part just gets easier and easier. So, what is a bubble sort? A bubble sort, in my understanding, is that it is going through different passes, and then for each pass, it will make one. I would say if you start from 0, then it will have 5. So the first pass, when it's first pass, it will give it will push the largest number to the fifth slot in this case, and then the second pass, it will push the second last one. But yeah, you know what? Let's actually get into an example and see how that goes. Okay. So the algorithm bubble sort is something like this. So the first pass is so we have original array like this. So 5, 1, 4, 2, 8. Okay. The algorithm works like this. So you start from the first one, and then you compare the first one with its next one, right? So in this case, 5 and 1, right? And since 5 is larger than 1, then we perform a swap. Swap means just exchange the position of those two numbers, right? And then you perform a swap. So what happened is that 5 is swapped with 1, right? So right now the list becomes 1, 5, 4, 2, 8. Okay, so that is done. Then we are going to another iteration. So we are comparing again if 5 is larger than 4, because 5 is just swapped, right? And then you're just holding that you know, sort of index or whatever, and then you try to swap 5 is equal to 5 is 5 and 4, and then because 5 is larger than 4, then it is swapped, right? So this number here will be 1, 4, 5, 2, 8, right? And then you compare again 5 with 2, then if 5 is compared to 2, 5 is definitely larger than 2, right? And then you know, you exchange the position, and then you run again. Then you have 5 and 8, right? But since 5 is less than 8, so we remain the same, or we don't move anything. Okay, so that is the first pass. Did you guys understand? Okay, so seems like there's no question. Okay, so now these elements are already in order, then algorithm does not swap them. So that means that after the first pass, there was always a largest number that is fixed in the last index. Okay, and then you once again perform a second pass. Is 1 is larger than 4? No, then remain what it is. Is 4 larger than 2? Definitely. So you sort of swap 4 and 2, right? Is 4 larger than 5? No. Okay. So yeah, yeah. And is 4 larger than 5? No. And if is 5 larger than 8? No. Then it is pretty much done, right? And then after the array is already sorted, but our algorithm does not know it is completed, then the algorithm needs one whole pass without any swap. No, it is sorted. Then if there is no swap provided, then you can know that it is working. So yeah, I mean, this algorithm is one of the interesting ones, and one of the fun ones to watch. But yeah, is there any sort of questions before I actually get into code? This code can be pretty abstracting. Okay, so no problem. All right. Yeah. So in terms of code, bubble sort. You're passed in an array, right? So you are getting that for ranges equal to n-1. So for example, if the length of the array is 10, right? Then the first for loop just gives you from range to 9. Right, and then the second one will just be from 0 to n minus I minus 1, because the last I elements are already in place. That means why do I do that? Because when n is equal when I is equal to 0, right? And then the range does not change every time you loop. So doesn't yeah. And then you have this if cases, which is just performing a swap, right? So if swap is so if the current object that you want to swap is actually like it is actually larger than the next elements, then perform swap, right? And then this swap in the swap idea in Python is very, very easy, because you can thanks to the tuple packing technique and unpacking technique, then you're just sort of pack it using a tuple, and then unpack it using this to perform the switch. Okay, so yeah, the last element's already taken place, and then another consideration is that you don't want to overshoot or like get outside of the bound, right? So that is that. So if I run this, then, you know, the sorted array is 11, 12, 22, 25, 34, 64, 90, right? And as you can see here, this is in random, you know, random situation. And then, yeah, in terms of performance of this algorithm, the best case scenario is ON, because when everything is sorted, then you only have to like go through it each time to check if it is actually sorted, right? But if you provide a you know, sorted list, then the algorithm can be as fast as ON. But in average case and the worst case, there will be n squared time. And the reason for n squared time is that, you know, you have 2 for loops in your algorithm. And, you know, those for loops are actually considered as n squared. So, yeah. Okay, so that is the algorithm. I will give you let me see. I will give you 10 minutes. Okay, I will give you 10 minutes to actually go through it by yourself, and then sort of you know, review a bit about you know, bubble sort. Okay, yeah, in terms of today, I am only prepared, no, I'm just want to give you, because we have like quite a few materials today. So yeah, I am just not gonna do it too quickly, because in terms of this sort of topic, it can be pretty challenging to understand and to think, even though like this is like 4 lines of code. Like it has more comments than code itself. So yeah, think about it. Think about this. Every pass of bubble sort, what bubble sort does, and then you know, think about the performance and think about the actual code. Whether you know how to rebuild it, or you know, whether you understand what is going on in that code. Okay, so I will give you 10 minutes. I'll give you until 49 or maybe 40. Let me see how, okay. Yeah, I will give you until 49, and then I will just watch a lecture. I will just watch a, we will just watch a video of selection sort, and we will leave everything until tomorrow. Okay, that sounds like a valid plan. All right, so yeah, think about it. If you want to go ahead and type this algorithm again, that works, right? And then if you want, you can really in this for loop, you can actually print this array out and see how what is happening, right? So if I do something like this, print, right, and then I sort of comment out this, run. Oops. Okay, so that is a large list, but you can sort of see what is happening. You can do print pass, and then right. So in this way, you can very easily see what is happening. So you have those as a whole bunch of number. Yeah. So what is happening here? Oh, I see what is happening. Let me actually change the order here. So here, if I print it, yeah, here you go. So at the start, we have 64, 34, 25, blah, 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 this list, right? And then you're gonna do, I take 64, and then I swap with 34, right? And then I take 64, swap with 25, right? Because 64 is larger than 25. And then the next one is 12, then we swap with 12 as well, right? The next one is 22, we swap. And then the next is 11, we swap. And we are guaranteed that, you know, after pass 0, then we are guaranteed that this n, this last element is the largest element. Okay. Yeah, we are guaranteed that the last element is the largest element. And then, you know, after pass 1, we are again will guarantee this one will be the second largest. This one will be the second largest, and then you know this. Like, did you see the pattern over here? So this is saying like, yo, when the first pass, then this will be just automatically be 90, right? Because you know, at the end product, this will be 90. And then at the end, this will just be 64 all the way, right? Because, you know, you just sort of have 64, right? And then 64, and then you're trying to slowly sorting. And right now you found 34, right? 34, right? And then you do 34, and then you start from the top, and then move slowly this 25 all the way to here in front of 34, and then you just do like 12. You know, you swap this. You perform this sort of swap, right? Swap 12. The swap was you know, you have 12 this, and then you have 12 22. You don't swap, and then you have 12. You have 22 11, right? And then you just sort of swap 11 and 22, and then you just once again after this is swapped, then you can compare 12 with 11, and then you just sort of swap it, and then finally, you know, you just find all the passes. Okay, so that is what is happening. And I will just tell you a little bit about this. So print ARR. So I can comment out this. I can comment out this. Okay. And then if you sort of print ARR, then yeah, this will give you the end result, right? And right now, what I'm gonna do is I'm gonna copy this and make it to I will do here. So ARR1 is equal to this. R1 dot reverse. print ARR1. I'm just gonna double check it. So this is now reversed, okay? And then for bubble sort, this is the worst case scenario. When a reverse is passed in and it is a list is passed in and is actually you know, order in the opposite order, then you will know what is happening. You know, it is sort of worst case, but like, yeah. So as you can see here, the average case is sort of like the worst case, right? But like this worst case needs the most amount of operation, right? Like you're basically swapping. Like you're basically swapping 90 from the first element to the last element, and you're swapping 64 from the first element to the second last element, and you know 34 to here, right? And then so on and so forth. Okay, so yeah, that is the idea of this bubble sort. And then, you know, because it is called bubble sort, because it is popping out a number like a bubble, okay? It is popping out the largest number like a bubble. It is sort of like all the way down in the water and then slowly popping out and then all the way to the top. And then by I mean top, I mean on the right side, right? So you're like popping a number every time from the left to the right. Okay, so that is the idea. Yeah, actually, what I should do is I should actually print it out here, and I'll print origin list. Print AR1. Okay, this is much more clear because if I print it here, then this one will actually be past 1, but you know this is a more clear idea, right? So this is the original list, and then you compare it, you swap it, compare it, you know, compare it, swap it, compare those two, swap, compare those two, swap, right? This is a much more clear, you know, way to do this. And then if you want to see the best case scenario, if you want to see the best case scenario, then you can do array. Oh, it is already sorted. So you can directly call bubble. You can directly copy this line and then paste it here. Yeah, I mean, it still checks, but like, yeah. All right, fine. Yeah, but it basically just goes through this loop. But yeah. Okay, so I would say I will call it that is it for bubble sort. If you have anything that is not clear, you can ask me about it after the class. Okay, so I will make you guys watch the video of selection sort and think about what the algorithm is, and then I will call it a day. Okay, so yeah, that was the video for selection sort. As you can see, it is pretty long, so that it is automatically in 2x speed. I didn't even address that the video is original in 2x speed. So yeah, as you can see, it is basically you know, taking out taking out the minimum value among all the lists, and then sort of placing it at first, and then keep doing that until the end. So it is like a typical n square algorithm, and then yeah, we are just gonna, you know, study it in the next lecture, and yeah. And then I'll probably give out a assignment later today, later tonight, and then you know, just sort of give you guys a little bit more time. So I will just make the deadline Sunday 23:59, so that you get like 4 or 5 days to work on it. Okay, so actually 4 days to work on it. I think it should be sufficient. And yeah, so that is my plan. If you guys have any questions, reach out to me. Otherwise, you know, that is the end of today's lecture. Yeah. So that is the end of today's lecture. I hope that everyone have a good day. Okay, sounds good.
Thank you.
Yep. Thanks.
Good day. Bye.
Yep. See ya.